this is the heading that you made. Now yesterday, we looked at this whole idea of general solution. So before we actually move on to this, let's just review. Let's do it all in radians. The first one that we did it for was tan. Okay? So I'm actually going to extend it a little bit. Let's say tan x is equal to some constant, c. Okay? So for instance, we looked at the example tan x equals 1. We looked at tan x equals 2. If this is the equation that you end up with, right, the actual solutions, the general solution is in the form x equals, now, how did it start? This is the simplest one, right? It was n pi, right, plus, now, we said theta, where theta is the related angle, okay? Now, if we know that tan x equals c, I can be a little more specific, and I can say that theta is actually tan inverse of c. For instance, tan inverse of 1, or tan inverse of 2, which is 60 degrees, something degrees, okay? Now, the reason why I'm sort of being cautious with this, I didn't show it to you yesterday, is because inverse trig is its own big topic in sort of end term 3 and term 4. Believe it or not, there's lots of things to be careful with it. However, this is sort of practically speaking how you're going to get that angle, okay? So you're going to get your calculator out, and if this is tan x equals 2, you're going to say, well, what's tan inverse of 2? And then that gives you a result, okay? It's like 1.11 or something like that. So that was for tan. The next one we did was cos, okay? So if that's equal to some constant, then its general solution is in the form. Now, think. Yeah, good. So because the period of cos is 2 pi, right? Instead of n pi, this is going to be 2 n pi. And then every time we went 2 pi forward, 2 pi forward, 2 pi forward, yeah, you had to go a little bit to the left and a little bit to the right, right? So this is going to be plus minus cos inverse of whatever that constant is. Okay? Last one, sine. And this is the really clever, sneaky one, right? We got that for sine, for some values you go forward, and some values you go backward, right? So for the even ones, you go forward, and the odd ones you go backward. So that's why we introduced this really clever switching factor, this minus 1 to the n, right? Which as you increment up, you go n equals 0, 1, 2, 3, 4. This will go positive, negative, positive, negative. Really, really smart way to do it. And your theta, in this case sine inverse of c, will hang on the end. Okay, now, these are the general solutions, but we want to be able to use them to actually generate a whole bunch of values for 2 reasons, okay? I sort of alluded to this yesterday. Number 1, sometimes part A of the question, you know, part 1, will be, tell me what the general solution is, express it in this form. And then part B will be, okay, now give me the first 4 values, right? So how do we go about doing that? Sorry, before I do that, the second reason is so you can check your answers, which we'll get to in a minute. How do we actually generate the values? What I recommend is that you draw up a table. So this is just to make sure that you don't miss any solutions. Okay, so let's just take a simple one. Let's go cos x is equal to root 3 on 2. Okay, so the general solution for this, x is equal to 2n pi plus or minus what? Pi on... Is it pi on 6 or is it pi on 3? It's 6. It's 6. Okay, so there's our general solution. So there's our part A. Now what do? Draw yourself up a table. And in this case, it's going to have 3 columns. Okay, you'll see why 3 in a second. I'm going to have 1 column for the values of n. Right, by the way, I should have been, I was a bit sneaky. And I forgot to introduce, okay, what our n was. You've got to say it's an integer. Okay, so now I'm going to put together a table with my n's in it. So usually it's customary to start with 0. Sometimes you might want to start with like -2 or -1, just depending on what domain they ask for. Okay, but it's sort of ordinary to start at 0, 1, 2, 3 is generally enough. Okay, now these other 2 columns, what do they correspond to? They correspond to the different solutions that are going to come out of this general solution. Because remember that plus or minus is really just shorthand to say this or this, right? So one of them will be 2n pi minus pi on 6. You'll get one set of solutions from that. And the other one will be 2n pi plus pi on 6. And we'll get a different set of solutions from there. Okay? So for instance, n equals 0. This one's going to be 0 minus pi on 6. So there's one answer. Okay. This one's going to be 0 plus pi on 6. So there's another answer. Okay, and then you keep on going. This is going to be, when you go for 2 pi, right, one lot of 2 pi, that's 12 pi on 6. 12 pi. So going backwards one will give me 11, and going forwards one will give me 13. Okay, and you can see how the pattern works. So this one will be 18, so backwards will be 17, no, sorry, that's wrong. I don't want 18, I want 24. 24, so I'll have 23 pi, and 25, and then this is going to be 35, and 37. Okay, so once you've drawn this up, for instance, suppose part B was not give me the first 4 answers, but it might be give us the answers from, you know, rather than say 0 to 2 pi, it might say something a bit different, like say pi to 3 pi, any domain you like, right? So you have a look through it, and you're like, well, okay, which ones match up? If my domain was, say, pi to 3 pi, okay? Well, these first 2 answers are both outside the domain, right? So I can ditch them. 11 pi on 6 is in there, so tick. 13 pi on 6, tick. 23 pi on 6, is that in the domain? 23 pi on 6.
It's 3 pi, right?
It's well, I want 3 pi, right?
Yeah,
so it's way over because 18 pi on 6 is where it ends. So I'm already outside the domain here. Okay. So now I know these are my 2 answers, right? So I would say for this specific domain, pi to 3 pi, x is equal to these 2 answers only. Okay. So there's just a typical example.